So today's lesson focuses on tectonic plates, what Earth features can be formed by the movement of tectonic plates, what is the internal Earth process that causes plates to move. We're going to talk about some scientists who contributed to our knowledge of plate tectonics, and then what happens. So this is where we get into the volcano and earthquake end of things. What happens when plates move? Okay, in lesson 2.1, we start out with our concept map here. We're looking at the Earth's crust. So in class, I asked students to identify, here are the 4 major layers of the Earth, A, B, C, and D. Which one of those is the Earth's crust? And students that selected D were correct. So this outermost layer is considered the crust. Think of it like the crust on a pizza. It's the outer kind of edge of the pizza, and so this is the outermost layer of the Earth. This is our crust. It's followed by the mantle, which we'll talk about more later today, and then the inner and outer core. So this is the inner core and the outer core. These are very, very hot areas, and they contribute to this process that's going to heat the mantle and then move our crust. So let's kind of dive back in here and talk about the crust specifically. The crust is made up of plates, and those plates can move, and they can move in different directions. So if the plates move apart, we're going to see this formation of seafloor ridges. We'll get into that in detail in our lesson. If they slide under each other, we can have volcanoes form. If they slide alongside each other, we'll see earthquakes form. And if they collide, crash into each other, we'll see mountains form. So those are the type of movements that we'll be looking at in our lesson. Lesson 2.1 starts out by going over some of the history. How did we know that plates existed in the first place? If you look just down at the ground, if you stand outside and you look at the ground, it's not obvious that there are different plates and that those plates have motion. But if you start to make a greater set of observations and kind of look on a global perspective, geologists notice things that earthquakes, volcanoes, and valuable minerals like gold and silver existed in particular locations. You couldn't find them equally distributed all over the Earth, but they seem to occur along the edges of continents. So I highlight that making observations is an important part of science. It is a good skill to be able to look at things and notice details, notice the intricacy, notice that things are different in different places. And I always like to point out that there's still lots of observing to be done. So science today is making great progress, but we continue to make more progress. We continue to understand how things work better as people make observations. So Alfred Wegener is the scientist that we're looking at today. He was credited with doing a lot of this work about understanding the continents and even coming up with this idea called continental drift. And this was his model. So he proposed that these continents that we have, that we live on, that they were moving around and drifting over time, and that at one time they had actually been together. And you might have learned about Pangea sometime in middle school, maybe even back in elementary school. Pangea is when we believe all of the continents were once kind of all pieced together. And based on where those plates are, we can see that cracks formed and rocks broke apart. And then with the movement of the plates that we're going to talk about today, those plates shifted, those continents drifted into new locations, and they continue to drift today. Even though it seems like North America is where North America is, it actually is moving. It's very, very small movements, and it's very, very slow, but it is measurable, and it's something that scientists are able to observe. I put hashtag test question down here on this slide because there are points on this slide and information that you will see pop up on tests for chapter 2 and even the final exam. So I like to highlight those things as we go along. I think they're important for you to know as you are preparing to take your graded assessments. Okay, another thing that we've learned through observation is that the rocks or the crust of the Earth is not the same all over. So the continental crusts, that's a continent like North America here, South America, the African continent, the Eurasian continent, which includes both Europe and Asia, the Australian continent. These continental pieces of rock are different than oceanic rock. And so oceanic rock would be like here in the Indian Ocean, the Pacific Ocean, the Atlantic Ocean, the plates or the rock that is under the water is different from the rock that's here above the water. And here are some of the distinct features. So oceanic crust has been observed to be thinner, younger, and denser than continental crust. Also, we have observed that the ocean crust is made of more igneous rock. That means it comes from volcanoes, while the rock that is making up the continents that we live on tends to be more metamorphic. That means that these rocks came from deep within the earth and they've been changed by heat and pressure. We will spend more time talking about the types of rocks, igneous, metamorphic, and even the third type, sedimentary rocks, when we get to Unit 3. But it's a good idea to know that the origin of continental rocks and the origin of oceanic rocks have to do with the way that the rocks were made in the first place. Okay, this moves us along to lesson 2.2, where we look at how did Wegner come up with this idea? How did he come up with the idea of continental drift? Well, he started first to look at fossil evidence and look at rock evidence. So I'm looking up here at our concept map, and this evidence suggested to him that maybe there was a supercontinent. And when he followed the evidence and when he followed the way that those continents could have possibly broken apart, he saw that they may have shifted into two separate pieces, and one of those pieces eventually became the continents of North America, Asia, Europe, and Greenland, and that second piece broke into the continents of Africa, South America, Antarctica, and Australia, and we'll look at some of that evidence in the form of fossils that he saw. I'm going to put a link to this in the comments. It is another YouTube video. It's from BrainPop, and it's called BrainPop Plate Tectonics. It is a good video that kind of covers all of the information that we're going over today. So if you like kind of quick reviews, I really like the way that Tim and Moby go over these things. So I'll put that link below in the comments. In class, I asked students to go over some of the pieces of evidence, so you could have gotten that information from the lessons. I'm going to go over my answers with you here, and this is some of the evidence that Wegner used to come up with his idea. And the first is the one that is, usually the one students think of first. The continents seem to fit together. So if we look, and South America and Africa are probably the best example. You see that the pieces or the shape of South America seems to fit really well, just like a puzzle, with the shape of Africa. And you can go through all the continents and actually get them to kind of mesh together, and we find that they do fit together really well. So this idea of plates breaking apart and drifting seems to be upheld by this piece of evidence. The next piece is maybe even more important. It tells us that fossils were similar across continents. So when you dig up fossils and you look at the age of the fossils, you look at the DNA of the fossils, and back in Wegener's time, DNA evidence wasn't available, but now we have that and we can sort of add to his information. But we find that fossils of different species, even things like plants that don't pick up and walk to a new place, they were found in very distant areas. So there are fossils from plants in Australia that are the same as fossils in South America, Africa, even Antarctica, where it's really frozen and cold, and India. Why would plants have been able to live in the very different climates that these places are today, and very distant places that these are today, unless at one time the continents were actually connected? Maybe that land was all sort of one big piece. And so fossil similarities across continents are one piece of evidence that tell us that, yeah, probably the continents were all connected at one point. Also, when we look at the rocks, we see that there were similar climates when these rocks were together. So in ancient times, Australia was probably very similar in its climate to Antarctica, whereas now Australia tends to be a pretty warm, dry place. Antarctica tends to be an extremely cold place. The reason that the climates are very different now is because they have very different locations on the planet. Antarctica's down at the South Pole. Australia's closer to that the tropic regions, and so it's got very, very different climates. But because in ancient times, when we look at ancient rocks, we see that the climates that were preserved in those rocks are similar, then that tells us that, yeah, maybe these continents were close together because they had similar climate patterns. The last piece of evidence was that features like mountains continue across continents. So we see mountain ranges in India continue into Europe and Asia. We see mountain ranges from continents that are not connected, but if you put them back together, almost like you were putting a puzzle back together, you would see that those features do continue. So these are the main pieces of evidence that tell us that continental drift is probably the thing that caused the continental plates we know today to move to the positions that they're in. Okay, this takes us into lesson 3, which asks, how do the plates move? How do continents drift? And it all has to do with the Earth's core. The Earth's core is very, very hot, and it heats the mantle. The mantle was that layer that was just underneath the crust. So crust was the outermost layer, then we went down into the mantle, and then the outer and the inner core. That core creates differences in temperature and differences in density across the upper mantle. So the mantle is going to be heated by the core of the Earth. That mantle is going to cause, or that heating in the mantle is going to cause something called convection. So we'll talk about that next. And convection is going to cause movement of our plates. So one of the things that we need to focus on in this lesson is how temperature and density can tell us about movement of tectonic plates. Okay, so let's take a look. I have an example on the left, and I kind of show you how that example applies to plate tectonics on the right. So let's talk about changes to temperature. If you were to heat a pot of water on a stove, the hottest point in this situation would be at the very bottom, closest to the heat source. So that water that's being heated most directly, kind of closest to the bottom of the pot, will eventually rise, because when we go back to think about things that you might have learned in chemistry or physics, hot air rises, things that are hot become less dense. So when things heat up, they expand, and as they become less dense, they tend to move upward. When things cool down, they become more dense and they move downward. And so what happens is those hot water molecules heat up, they move upward. Now that they're away from the heat source, they begin to cool down and they move downward. And so this creates something called a convection current. This is a really, really important term, and you're going to see it over and over again this trimester. So convection currents are caused by a heating and cooling circulation pattern. If I were to take this hot pot of water and put 2 wood blocks on it, you would see that the wood blocks would actually move outward toward the edges of the pot, and they would do that because of the movement caused by these convection currents. If we move up to the bigger scale and we look at the Earth in general, if we were able to look inside the Earth, we see the same process happen in the mantle. So the core acts like the heating source. The mantle is rock, but it's actually molten in nature, so it kind of acts like a putty, and it heats up, and the hottest stuff moves upward. It becomes less dense. As it moves away from that heat source, it cools off, and it moves back down, and then it gets heated again, and we see these convection currents take place. Those convection currents are able to move the crust or move the plates that are above them. And so we see this outward movement on both sides of where these convections currents occur. And then upward, sometimes we can even see volcanoes form because that mantle can be so hot, it can erupt out of the surface. So we're going to take a deeper look at convection. If we kind of take a snapshot of the interior of the Earth, we see those convection currents can cause volcano formation. They can also just cause that mantle can come out and cool down quickly, and that creates young rocks that push away the older rocks. And so we notice that under the ocean floor, we have these kind of layers of rock ages. The youngest rocks will be in the middle, and they get older and older as we move away from those these mid-ocean ridges or these hotspot areas. We also see that plates sometimes slide underneath of each other. We'll get to this in a few slides. And then we have continental and oceanic plates that can collide, and we form features like volcanoes and mountain ranges. So let's talk about how that works coming up here. One last thing I wanted to point out, and this is a test question item, so that's why I have a separate slide on this, is that in addition to these convection currents, there's another thing that can cause plates to move, and it is the plates themselves. So just like if you were to set a table and you had the tablecloth kind of hanging over the edge, if you put your dinner plate and some utensils on the edge of the table, but the tablecloth was really heavy and hanging down. If that tablecloth started to slide down, it might actually pull all of this stuff off with it. So like the weight of the table, or the weight of the cloth kind of pulls the materials off the table. The same sort of effect can actually happen with plates.